Hi everyone! We're going to talk about just properties of metals, nonmetals, and metalloids, as well as talk about some of the characteristics of the families for the periodic table. The families that we're going to talk about are, I think, the characteristics of the families that you need to know for your AP test. I maybe like not next week, but as we get into chapter 8 and 9, kind of pull a little bit of extra information about some of these families as we start talking about bonding. And I'll do that from like chapter 22 or 23 from your book, but I'm just going to pick and choose what I think will be relevant for us. But we won't get into that until like chapter 8 and 9, which we're going to next, okay? So first of all, if we're just talking about metals, nonmetals, and metalloids, let's really just focus on metals right now. I know that the metals take up a majority of the periodic table. And if I think about just metallic character, just meaning that, and how do we know what metallic character is? The more that an element will exhibit physical and chemical properties that are like a metal, that means that we're going to have an increase in an element's metallic character. So the more physical and chemical properties that we have, that an element has, that are very similar to a metal, then that means it's going to have an increased metallic character, okay? So metallic character is going to increase as we move from right to left along the periodic table, and then it's also going to increase as we move down the periodic table, down a group or down a family. So again, we'll see that a majority of our periodic table is metals. We have our small little portion here of nonmetals plus hydrogen over here, and then our little metalloid family there. If we talk about properties or characteristics between metals versus nonmetals, we know that metals have a shiny luster. They can come in a variety of colors, but most often metals are very silvery, very metallic in their color. They're usually solids, and those solids are malleable, and they can also be ductile. But what does that mean? So malleable just means that we can kind of pound it into thin sheets, and then ductile will mean that we can draw it into thin wires. So malleable, it can be pounded into thinner sheets. Ductile can be drawn into thin wires. Okay, we know metals are good conductors of heat and electricity, and we know this because they have those sea of electrons. And those sea of electrons just allow the electrons to not be very localized around one particular cation. They're able to move freely amongst all of the cations that are there in the metal, okay? So they're great conductors of heat and electricity, and that's because of the sea of electrons. Most metal oxides are ionic solids, so most often we see that metals will form ionic compounds, and usually if we add or react these metal oxides, they typically will form some type of basic solution. And then if we try to dissolve these metals in a type of solution, we know that metals typically will form cations. If we talk about nonmetals, they do not have any type of real luster, and they are various in their color. If their nonmetals are solids, then those nonmetals are very, very brittle. And they also, I could have some nonmetals that will form what we would call network covalent compounds or network solids, like diamond, for example. And those can be very, very hard, and some of them could be very, very soft. So really it just depends on what type of nonmetal that we're talking about. But there are specific nonmetals that we'll focus on later on once we get into like chapter 12 or 13 or one of those chapters. And we'll distinguish which ones will particularly be very difficult to break versus which ones are brittle and soft. We know that nonmetals are poor conductors of heat and electricity. They do not have those sea of electrons. Instead, ultimately, nonmetals typically have just covalent bonds. A lot of them just have the London dispersion forces that are holding molecules of them together. So really, nonmetals, because they don't have that sea of electron, are very poor conductors of heat and electricity. Most nonmetal oxides are molecular substances, but again, we do have some nonmetal oxides that will form what we call covalent networks. So again, diamond is one of those things, even though it's not a nonmetal oxide, but they don't always just form molecular substances. They can also form something called a covalent network. We don't have to know what that is yet. We'll keep that for chapter 12 or 13, whatever it is. And usually if we react a nonmetal oxide with something, usually we end up with an acidic solution. And finally, for nonmetals, we know they tend to form anions in aqueous solutions. If I'm talking about properties of metalloids, they're really going to be somewhere in the middle of metals and nonmetals. So if we added metalloids in there, they probably will go more towards the metal side than they will the nonmetal side, but they'll still fall. There's that spectrum in between. If we think about charges, we know that metals tend to form cations because they have such a low ionization energy. So I don't need to supply a lot of energy to those outermost electrons, because inherently that atom would prefer to get rid of those few, either 1 or 2 electrons, because then it will have that full electron configuration, that full outer shell. Versus nonmetals, which would tend to form anions because they need to gain those extra electrons. So if they gain 1 or 2 electrons, they'll have that full outer shell. So they tend to be anions. Okay, for metals, again, they're lustrous, they're malleable, they're ductile. Again, malleable just meaning that we could pound it into thin sheets, ductile, drawn into thin wires. Good conductors of heat electricity. All of them are solids except for mercury. All of them are solids at room temp, except for mercury, which is going to be a liquid. And we tend to say that ionic compounds will form when we have a metal and a nonmetal. So an easy way to know an ionic compound is to recognize that there's a metal that's bonded. Nonmetals, dull, they're brittle for the most part. They're also poor conductors of heat electricity. Non-metal compounds nonmetals typically will form molecular compounds, and we know they could be solids, liquids, or gases. We know that as we move towards halogens and noble gases, we get into more of the gas part, or the gas state of matter. And we have 7 nonmetals that are diatomic, and generally nonmetals have low melting points because they're really just held together by covalent bonds or really weak intermolecular forces. So it's not as hard to overcome that type of Coulombic attraction holding them together. Metalloids have some characteristics of metals, some characteristics of nonmetals. So this is an example of silicon. It looks really, really shiny, but it's very brittle, and it's a not very good conductor of electricity and heat. Okay, so getting into families, we have the alkali metals. That's group 1A. We know that they typically they do have a positive 1 oxidation state, or they will form positive 1 ions. They are very soft, metallic solids, and the name comes from Arabic word for ashes, and that's because when they react with water, they are incredibly violent in their reaction. So reactions with water are famously exothermic. So 2M just meaning my metal, specifically here my alkali metal. So if I react an alkali metal with water, I'm going to get an alkali hydroxide or a metal hydroxide plus hydrogen gas. So it's really this hydrogen gas that's creating this big exothermic reaction. They are found usually only in compounds in nature, and that's just because if we find them by themselves, well, we wouldn't be able to find them by themselves because they're so reactive with water that they would react immediately with water and air. So we always find them bonded to something else and not just in their pure elemental form. They have very low densities, they have low melting points, and we also know that the alkali metals have low ionization energies. And we know that their ionization energy is low because they want to get rid of that outermost electron because they want that full outer shell. And if they get rid of that one, they'll have that full outer shell. So it's not going to take a lot of energy to get rid of that one extra electron. Okay, all alkali metals will react with oxygen to form peroxides, and that's true except for lithium. Potassium, rubidium, and cesium will react with oxygen to form something called a superoxide. So a superoxide I see here is just O2. So I have K plus O2 is going to give me potassium superoxide, which is just KO2. Alkali metals are also responsible for a lot of